get started, just two quick announcements. We have an attendance quiz today, and then your exam 2B opens up today as well. You'll have 24 hours to do that. Again, same format, unzipped grade, and there's, again, another 5 bonus questions at the end. So for questions 16 through 30, don't forget to scroll all the way to the bottom. That's where you'll see the spectral data you need to interpret. Any questions before we get started with some other announcements? So one announcement, I guess, advisement opened up yesterday. So if you're considering a chemistry minor, a course you might want to think about taking on spring semester is spectral elucidation of structure. And that's a 3-credit course taught by Dr. Julie Pigza. Unfortunately, it meets at 8 a.m. I know that's a bit early for some people, but it's Monday, Wednesday. And so to get a chemistry minor, if you take Organic 2, this course, and then Chem Safety, which is another 1 credit hour, that gets you up to your 20 required for the minor. The prereqs for that course are this course, Organic 1, and sort of what it is a whole semester's worth of what we did in Module 2 here, where you really go more into depth about each of the analytical techniques to figure out structure. And there's I don't know how she's going to run it, but usually there's a project where you're given a data set, and so you analyze that data set, you write up a little report. You work in small groups, maybe 2 or 3 students, and it's kind of fun, I think. As mentioned here on the slide, it's like figuring out a puzzle. So you need to make sure all your data fits, and then you come up with a structure, you do the assignments. So that's something to consider. She also records her lectures using WebEx and posts them in Canvas. So that's another bonus, I guess. So that's, again, a course to consider if you like doing what we're doing now and if you want to pursue a minor in chemistry. The other thing I want to talk about just briefly, so last fall I was given $300 to buy the SNATM kits, which I'll show you in a minute, from the USM Center for Faculty Development. And so my proposal for that was basically to get you all as undergraduates involved in sort of paying your education forward by creating a small or a short video, 3 to 5 minute video on taking a molecular formula, talking about the atoms involved in that molecular formula, so hybridization, the functional groups, some physical properties, that sort of thing. And then for the most part, you're taking that kit and building it as a way, an educational activity, which I'll post those videos on YouTube for other people to see. So if you're interested in doing that, this will be for bonus points. I'll have to sort of reconfigure the announcement in Canvas from last fall to this fall. But I'll try to post that by Friday. And basically what you'll do is look at the table that I have, pick a molecular formula, propose a structure. I'll approve whether that molecule's been taken. I want everyone to do a different molecule. I don't need 140 videos of ethanol. And so that's to get some diversity in the structures. But this was the impetus for some other outreach that we do. So the SNATM's kit was made by Derek Muller, and if you troll around YouTube, you've probably seen his channel, Veritasium. He has a PhD in physics education, And so he developed the snatoms, which you see ethanol is sitting on his head there. In this model kit is very different in that it uses magnets to form the bonds. And so this is sort of the first kit that I've ever seen that's like that. And so this is what they are. That's the periodic table of what's in here. So the hydrogens are white. You can see there's like, it's a ball, but it has one flat surface. And then in there is that little silver magnet. And so they just like snap together. So since it's a sigma bond, it can rotate. Carbon is the black ball. It has 4 surfaces. So you can stick 4 hydrogens on it. You can hear the snap. That's the bond being made. Like, it's not a gym bro or anything, but you pull it apart. It takes a little bit of force, and that's the bond breaking. And so you make a little video on your phone. You talk about the molecule, atoms attached to atoms attached to each carbon, the functional groups. So there's nitrogen in blue. That has three bonds. Oxygen is red, that has 2. These other ones are for like transition metals and whatnot. But basically, there's, I think, 25 videos that you can look at on YouTube already of students that have done this to get an idea of the flow of the video and sort of the production quality. Some of them are very good. Some of them are not very good. But I don't critique too much on that quality as long as you put the effort in sort of certain points to do it. So the bonus assignment is basically from that table, you'd identify what carbon count, 5 or 6, you want to choose from, and then what elements in there, and then from that, you're going to propose a structure. And then I'll approve that if no one's done it, and then you create your video from it. And let me see. And then you just build your molecule. And so that's one sort of outreach activity. And if you're part of the ACS club, we actually go to like schools. We have 20 of those kits. We let the students go through, we lead them through a demo which they build molecules from, and then we give them a smaller version to take home. So that's sort of outreach that's required for many purposes, but it's a way to sort of pay forward what you've learned in this class to other K through 12 students. So look for an announcement in Canvas. There'll be the announcement, and then there'll be like an assignment with all the instructions on how to follow through with that. So this is a slide that you'd make to sort of introduce the molecule. So this is the slide. Again, once you figure out your molecule, you just look some stuff up, fill the table in, edit your video, submit it to me, and then I upload it to YouTube. Any questions so far? So we'll spend like the first part of the lecture doing some problem solving with the IR, mass spec, and NMR that we've learned, and this should help you for the exam today in terms of the thought process. And then the rest of the lecture is just sort of for your own information about sort of the next step with spectroscopy. That would give you sort of a preview for that other 404 course. So what we'll do is look at these pieces of data here, pull out some fragments, and then we'll piece those fragments together to make a structure. And then the next slide, the data is presented to you in a little bit different way from some problem sets on a website that are linked in Canvas that you can use to sort of practice this as well. So this data comes from a book of problems. There's just they look like this. There's like 200 of them. And so we're going to pull out these pertinent pieces of information, see what heteroatoms there are. We know there's C and H. We'll do the count, get the molecular formula, do degrees of unsaturation, and then make a claim. So let's look at the IR and mass spec first. In the IR spectrum, in region 1, we don't really see any broad peaks that would be indicative of, say, OH or NH. We have a sharp signal in region 2 at 2249 wave numbers. And then region 3, we don't really see a signal there that would be a carbonyl. So we have region 2 to consider. And then in the mass spec, the parent ion M plus is at 147. And then we have this other signal, 149. It's hard to see, but the intensities are equal. So from these two pieces of data, what heteroatoms do you think are present in the molecular formula? Nitrogen, why is that? So the mass is odd, 147. The parent's odd, so that's indicative of nitrogen. And what else can we pull out of that data? So there's a bromine, because the 147, that's the parent, and then 149 is M plus 2. So because that's a 1-to-1 ratio, that's bromine. So I'll say M to M plus 2 is 1-to-1. So that means we have a bromine. Then if we go back to the IR, that signal there at 249, because we know there's nitrogen, what is that signal telling us? C triple bond N. We know that there's nitrogen from the odd mass. Then in region 2, that's the triple bond region. So we can say that that fragment is equal to C triple bond N. So far we have two fragments, a nitrile and a bromine. Now let's go over to the carbon NMR. So if we look at this bottom one first, it says proton decoupled. That's just the normal carbon NMR. We're going to ignore the solvent signal. And then on that spectrum, how many signals do you see? 4? So one thing to always keep in mind, that the carbon NMR is telling you the unique number of carbons. That does not necessarily have to be the total number of carbons, because if there is symmetry, you're going to see less signals. So now let's take a look at the spectrum that's stacked above it called depth. And what that is, the attached hydrogens. So if we're reading, let's read from left to right. The signal at 120, if you look above, do you see any signal on that stacked spectrum? So there's no signal there, right? So there's nothing there. That means that carbon has no hydrogens attached to it. So we can therefore conclude that that signal belongs to the carbon of the nitrile. So see how that carbon has triple bond to nitrogen, then it's bonded to something else. It can't be hydrogen. So we can make the assignment that that is an sp hybridized carbon. Then we have three other signals. Now using this key, where CH2 is phased down, CH and CH3 are phased up, how would you then classify those remaining three signals? What type of carbon atoms are they? So they're sp3, and they have how many attached hydrogens to them? They all have 2. So they're all CH2 groups. Now, if we look at the proton NMR, how many signals do you see there? So there's 3. And then what you see over here is just the expansion, so you can see the multiplicity of that. So we know based on the proton or the carbon NMR data that the ratio of these 3 signals has to be 2 to 2 to 2, right? Because that's what that depth data is telling us. This extra line that you see, that's the integration curve. And again, that's just telling you the ratio. So the ratio is 2 to 2 to 2. And so when we put all that together, these are the fragments we have. So we have 5 fragments. The fragments that only have like 1 attachment point, like you could not bond those together, right? Because if you did, then you'd leave out the other 3. So basically we have to string together the CH2 groups and then stick those single fragments at the end. So we'll have CH2, 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 and then at the end we put those other fragments, bromine, and then the nitrile. Do you have a question?
I was wondering, how do we know that the CH2 is an sp3 and an sp2?
So the question was, how do we know that these 3 carbons here are sp3 and not sp2? I'm going to say about 80 parts per million in the carbon. So 80 to 0 has to be sp3. An sp2 hybridized carbon that had 2 attached hydrogens would be, say, like 100 to maybe like 150. So that the overlap of 80 to 100, that's where you see sp and sp2. Once you get past, 80, so 80 to 220, you cannot have an sp3 hybridized carbon. So the location of the signal does indicate to you the hybridization. And then the depth spectrum also helps you figure out the attached hydrogens. And so one of the skills of solving these is you have to hop back and forth between the different pieces of data to make sure that you're not proposing something that can't exist. So the molecule is, if we number it, this would be 4-bromo. It's 4 carbons, butane, and then nitrile at the end. So 4-bromo butane nitrile. So questions 16 through 30 on the exam relate to structure, like this sort of problem solving. So you'll see these sort of questions presented to you, individually, and then you refer back to the data, and there's questions that are not asked, but you sort of have to ask them yourselves to figure out ultimately what the structure is. So there's some implicit things in there where you have to piece this data together. But overall, I think the problems are manageable if you understand this logic. Any questions before we move on to the next one? Yep. Yeah, you could do that piecewise as well. So as an example of that, since we know that from the mass spec there was a bromine, so the bromine was 79. We know there's a nitrogen from the odd mass plus the IR stretch. And then you could just look at the carbon data and say there's 4 signals, so there at least has to be a contribution of 48, assuming that each carbon is unique. And then you add all that together, subtract that away from 147, that should get you the hydrogen count. If you ever run into a discrepancy where you're doing that logic and it doesn't equal the parent mass, what that's telling you is there's probably some symmetry in the carbon count where the total carbon signals is less than what is in the molecular formula. So the next problem, again, is from this website. And that's linked as a page in Canvas under the Module 2. I think there's like 100 of these, easy, medium, and difficult, so you can, go through however confident you're feeling and sort of do the same analysis. So this was, I think it calls them tasks instead of problems, but task 1 under the easy. And here we're just given the proton and carbon data. So we'll ask some questions and try to piece together some fragments to figure out a claim from that molecular formula that we're given. So C4H8O2. Maybe the first thing we can do is figure out degrees of unsaturation. So C4H8O2, the oxygen does not affect the hydrogen count, so that's C4H8. For 4 carbons, there should be 10 hydrogens. So that's going to give us 1 degree of unsaturation. Let's look at the carbon NMR first. Again, that's a little bit easier to interpret. Ignoring this signal right here, which is solvent, how many carbon signals do you see? So there's 4. You see 4 signals. The molecular formula has 4 carbons, so each carbon is unique. So see this abbreviation here, APT. That stands for attached proton test. That's the same as that depth spectrum we saw in the prior problem. So things that are phased up, sorry, let me backtrack. This one's a little weird. The phasing on this one's opposite. Through no fault of my own. The phasing on this one, sorry, is reversed. CH3 are down. CH2 and carbons with no hydrogens are phased up. That will be explicitly stated to you what the key is on the exam, how the phasing is. So of the 4, how many signals are phased up? So there's 2. So 171 and 60. Based on the chemical shift of 171, what do you know about the hybridization of that carbon? It's sp2 hybridized. And then what about 60? What's the hybridization of that? sp3. So the sp3 hybridized carbon, based on the phasing key, has how many attached hydrogens? It has 2 attached hydrogens. What about the sp2 hybridized carbon down here at 171? How many attached hydrogens do you think that has? It has to have 0. So if it's sp2 hybridized, based on the region it's occurring in, what sort of functional group would it be present in? A carbonyl. So that has to be a carbonyl carbon. And then the remaining two signals, 21 and 14, those both have to be sp3 as well. So based on their phasing, do you think they're CH or CH3? So maybe we can gain more confidence in the answer to that question if we look at the proton NMR real quick. In the proton NMR, this signal here is solvent at 7.2. And then looking at the rest of the spectrum, how many signals do you see? There's 3 signals. So 1, 2, and 3. The number underneath, again, that's the integration. So that one is 2, and the remaining signals integrate to 3. So if we were to set up the uniqueness, there's 4 carbons, 3 unique sets of hydrogen, 2, 3, and 3. So now to get back to that other question about the remaining 2 carbons, those both have to be CH3 groups, because that is what this number here, 3 and 3, are telling you. So far we have, 4 fragments? CH3, CH3, CH2, and then CO. So we've accounted for all the carbons, all the hydrogens, and only one of the oxygens. So we need to stick an oxygen in there, and what is going to guide us in where it goes are the chemical shift values. See that signal at 60 in the carbon NMR? That is telling you that that carbon has to be bonded to a heteroatom because it's the furthest away from methane. The signal at about 4.15, which is blown up here as a quartet, that's the CH2 group that belongs to that carbon. So we know that because that's CH2, that integrates to 2, that the CH2 group has to be bonded to an oxygen. So we can revise that fragment. So there are the 4 fragments now we need to stick together. And so before I draw that out, if you think about it, what would the name of that functional group be in the claim that we're going to make? So it can't be a carboxylic acid because we've already accounted for all of the hydrogens. Huh? It's going to be an ester. See in the 3 unique proton signals? You have one that integrates to 3 and it's a singlet. So that's telling you that the neighboring carbon has no attached hydrogens, right? So one of these methyl groups is going to be bonded to the carbonyl group. So we can further revise Now we have those 3 fragments we need to stick together. And really the only way to do that, which will match the multiplicity that you see in terms of the quartet and the triplet, is that we have to bond the CH3 group to the CH2 group. So this then becomes CH3, CH2O, and then we bond that back to the carbonyl. So the final structure that we end up with is that ester that's shown. So maybe in this box, what I'll draw in blue so that blue structure could be another claim for an ester, but the reason why it wouldn't be the best one, again, is based on the chemical shifts. The multiplicities of the stuff in blue would still be the same, but now you see that CH3 group, which would be a singlet. The singlet that we're shown is at a chemical shift of about 2 parts per million. If it were bonded to oxygen, you would see that singlet more in the 4 part per million region. So again, when you're drawing your claim, you have to pay attention to that subtle detail of the chemical shifts to make sure that they match as well. So can you imagine if you were sitting in this class last fall, you'd have to do something like this during the 1-hour exam in class? So again, you have 24 hours to do the exam. Get out a sheet or two of paper, write your thoughts down before you submit your responses. Any questions before we get into like the last little lecture bit here? So the remaining slides, none of this will be on the exam. It's really more as sort of for your information of additional pieces of spectral data that are commonly obtained to really help nail down structure. And so this is important because, again, when the Food and Drug Administration approves like a prescription drug, the pharmaceutical company has to prove beyond a reasonable doubt that the stuff that's in that pill is that exact substance and not some isomer. So the data that we'll see is what is used to prove unambiguously what structure is. So for this module, we had talked a lot about this ketone here, 2-butanone. So there's the structure, there's the proton NMR that we've seen quite a bit. We have a methyl group, which is a singlet, a CH2 group, which is a quartet, and then the other methyl group, which is a triplet. So we can be pretty confident in those assignments. However, another type of NMR experiment that exists is called two-dimensional correlation spectroscopy. And what you're seeing here on the sort of the flat axes, so you have, let's say, X, Y, and Z. X and Y are the proton, and then Z is telling you the signals that are coupled to one another. And so this is called COSY, which is correlation spectroscopy. And what you see here is sort of a 3D representation of a signal. So you have proton on each axis, and then in the middle is sort of this mountain range where the signals are in 3 dimensions. What happens is you actually put your eyeball sort of perpendicular to the mountain range and you look down on it. And if you've ever gone hiking, they sell these contour maps of like mountain ranges. And so the contours are telling you the elevation of the hills or the mountains. And so that's how. So when we interpret these, we interpret this type of data. So here's your x-axis, your y-axis. You're then looking down on the mountain range at the contours. The red line or the diagonal is what you're used to seeing in just the proton NMR by itself. Then these other like blips or blobs or splotches or whatever, those are called the cross peaks. And what they're telling you is the signals that are coupled to one another in spin systems. If you can imagine taking that red line, and if you rotate it, I'm going to say that the top left and the bottom right are the same thing. They're kind of mirror images of one another. So if you rotate that, the stuff you see on the top left is the same stuff you see on the bottom right. So the way that this is interpreted is those signals from the top left to the bottom right, you connect them with another line. That tells you that the signals are correlated, which is an indication of the coupling, which is the J value. So if you're reading from right to left and you encounter that triplet, then you go down. The signal that's on the red line is that triplet itself. But if you go further down, you hit that blob. And then if you go back over to the left, you see that it lines up now with that quartet. So when you do that, it's telling you that those two signals are coupled to one another. And if you watch the screencast from Wednesday, when we talked about dihedral angles and coupling and that coupling constant distance in the spin system, that's essentially what that's telling you. So the H4 hydrogens are coupled to the H3 hydrogens. And as I said, if you keep scrolling along, you see you hit H3, you go down and then over. You see it hits H4. So that's the mirror image of it. So in all reality, you're just looking at sort of one half of that spectrum. So your normal coupling of neighbors has to involve 4 atoms. H, carbon, carbon, H. So you have your signal of interest, then you look at the neighbors, you do the n+1 rule to determine the multiplicity. So in common terms, basically what we say in lab is that they see each other. They see or feel each other, that leads to the multiplicity through the coupling. Probably the most powerful 2D technique is this one here, abbreviated HSQC. They give these things all sort of weird abbreviations. But what this one is telling you is how the hydrogens are attached to the carbons. So with that one piece of data, you get pretty much everything you need that you've already extracted from the individual proton and carbon data. You can see that these, orangish looking hills are phased up, and the blue one is phased down. So that's telling you that's a CH2 group. And then the other ones are either CH or CH3. So on the top axis is your proton. On the left axis is your carbon data. So the normal spectra you're used to seeing, sort of in one dimension, proton, 3 unique signals. Carbon, 3 unique signals. Even though that molecule had 4 carbons, what this experiment is only telling you is the attached hydrogens. Since that carbon there doesn't have any, that's why you're not seeing it on that axis. This one looks different in that there's no diagonal line, but you see these blobs again. So the 3 blobs, it's not in color, but you can sort of see that 2 of them are darker than the third one. And so what it's telling you in terms of the correlation of the contour is the hydrogens that are attached specifically to each carbon. So as we read over, we see that triplet. We go down, we see that blob. Then we go to the left, and we see the exact carbon atom that those hydrogens are attached to. So the singlet, we go down, and then over, we can say that that carbon is attached to the methyl group singlet. We do the same for the quartet, down and then over, and we've done the correlation between the C's and the H's. So the colors blue, green, and pink, are showing you the carbon atoms as the ball, and then the hydrogens that are attached to them. Again, the carbonyl carbon doesn't show up because it does not have attached hydrogens. And then the last one as we wrap up here is called HMBC. And this one looks different because it's not showing you attached hydrogens to a carbon. It's giving you information about the neighbors. So this is a 2 or 3 bond correlation. And for this molecule, it's not as complex, but this type of spectrum is used when you really start getting into some more complex looking stuff. You have a question?
Yeah, so the previous one was telling you the attachment to that carbon. And this one is telling you about.
Yes. So notice when we read from right to left, we hit that triplet and we go down. We said from the HSQC that was attached to that carbon, right? But in that region, you no longer see a blob. You have to go further down before you see one. But notice in that column, you have more than one blob because it's reaching out to all the neighbors that it can see that are within 2 or 3 bonds. And so from that, it's almost like a math problem where you get these little fragments. In the way that I teach it in my research lab is we use letters. You get like A, B, C, D, E, F, G. You get this series of fragments, and then you have to overlap them to get the carbon backbone. So really, it's a logic problem. So from H4, we went down, we saw a blob. Then we can go over and say, okay, that sees carbon number 3. Now, the other thing that's different in the HMBC is that you actually see the carbonyl carbons because it's telling you that relationship from that hydrogen to the carbons within a certain distance. So in the blue arrows, that shows you 2 bonds. The red is 3. And then we've just color-coded these different relationships from each signal. And so these are sort of the fragments, again, that I was talking about. So that H4 triplet, when you go down in blue, it's seeing carbon number 3. When you go down in red, it's seeing the carbonyl. So it's sort of reaching out along the chain to a certain extent. Again, the radio frequency can only go so far in detecting these relationships. And so you can do that for each column as you go down, then you go over through the rows, you get these little fragments, you piece them together, and that will ultimately tell you without doubt what that structure is. Yeah.
From the spectrum alone, can you differentiate which signal, I guess, comes from sort of like 2 bonds away or 3 bonds away?
So the question was, how do you figure out if it's 2 or 3? I'm not an NMR expert, but I think within this experiment, you can phase it a certain way. Even though this is black and white, the data that you're given is in color. I think you can phase those connections differently so it shows up as a different color, and it will tell you that information. Yeah. Yeah, so this signal right there is the carbonyl carbon. Yeah, the first one here, that's the CH3 at the end of the chain. The CH2 here, that's the CH2 that's next to that CH3 methyl group. So as you open up your exam and look at data, keep in mind how things are coupled in spin systems. Keep in mind chemical shifts to help you refute one claim or support another. So with that, we'll wrap it up. You have a quiz and an exam both due tomorrow at noon.